All right. Thank you very much for the introduction. Good morning. I will share my screen, the entire screen, share, and you should see here. So it's 10:15 for you. It's 9:45 at night for me. And I will go to my PowerPoints.
You can enable the recording also.
The recording has been running, even your part was already included in the recording. So I will make this full screen. Okay, so we are. My understanding is, I know from the brochure for the meeting. So this is we at the very end of a meeting that was the focus was material science rather than chemistry, which is sort of usually what Spartan deals with. So my first slide, I want to immediately make clear what we are going to deal with in the next hour. There are really two fundamentally different ways how you can approach calculations of condensed matter systems with quantum methods. The one that I suspect, if the majority of you actually probably are either material science or physics, the one that you are more familiar with would involve actually the description of crystals using a space group, and then carrying out a quantum calculation with plane waves as the basis set. This, the buzzword is these are band structure calculations. Famous programs that do that are, for example, VASP and CASTEP. So these are two big ones. There are some other ones, Quantum Espresso and so on. What we will be talking about, though, in the next hour is something that is complementary to it. It's different. Namely, we will be dealing with molecules or clusters of molecules. So periodic replication of the system won't come into the picture. So this is the buzzword, usually called either quantum chemistry or molecular modeling. Actually, I'm noticing I'm getting sort of a lot of feedback. Maybe I should use the headset. I will plug that in so I won't be that distracted. I hope you can still headset microphone. Yeah, I think it's better this way. So. Okay, so we were talking about real quantum chemistry as applied to material science problems. So since this all originates with molecules, so the basis functions are typically Gaussians, which are centered on the nuclei of the molecule. So this is what we will be dealing with. This is complementary, to the sort of the physics-based approach. It's the chemistry-based approach to do quantum calculations of condensed matter as opposed to the physics-based approach. So the program we will be using is Spartan, as Yatindra had pointed out. Which has tens of thousands of copies around the world. The most prominent use is always in organic chemistry. We won't really touch on this in the next hour, but that is sort of the bulk of the user base. In organic chemistry, material science is just you work with more elements from the periodic table. That's the main difference to organic. Biochemistry applications, there are quite a few of those too. We won't not talk about it in this talk. Here, this is a slide sort of when I talk about chemistry applications. What do people actually use the program for? So it ties in a little bit what Yatindra already mentioned. So evaluating compounds, what's the energy, what are the physical properties, getting an idea about something new that you might think of making or already made in the lab. So typically up to 500 atomic mass units, that's sort of the max. If you can go beyond that, but things will get very, very slow. I would say the pain threshold for running quantum calculations these days would be, if it gets into the more than an hour, a couple of hours. In the past, people would run calculations over a weekend or, a whole month or something like that. This was the past. Now people, it's sort of instant gratification on your laptop. You want the result in, not necessarily in a minute, but, an hour, a couple of hours at most. Identifying compounds, developing reaction pathways, sort of this classical chemistry. And a feature I will touch on at some point is that Spartan has a built-in strong support for handling lists of molecules. So you can look at more than one system at a time without having to go, through the same motions again and again and again. So I want to jump into the program before I get back to the PowerPoints and start Spartan. So this is when you install Spartan with your trial license. So this would be the very first screen. So an empty lab bench where you can assemble a molecule or something. So there are two. You can either you can build by using sketching mode, sort of what chemists do. Maybe material scientists are probably not that necessarily that versed in it. What I will try to do is here actually quickly build a common liquid crystal, 5Cb, cyanopentyl biphenyl. So 1, 2, 3, 4. Yeah, I have a pentyl group, 1, 2, 3, 4, 5. Yes, and then a cyano group here on the other side, and put the nitrogen, and then make this here a triple bond. Oops, I reversed that. So, and then I can click here on, now I've built a 3D. Here you see the 3D version of the molecule. So I will quickly, minimize that with a classical force field, build, minimize. So actually that not much happened here. I will, so that's, quantum mechanics hasn't come into the picture yet. I will, here, this looks sort of, if I go to the space filling style, here at the end of the molecule, this looks like a bad overlap. So I will go to ball and spoke. I can correct that manually. If I go to build, edit, and I'll select, oops, here. I will rotate around, sketch that. I could also do this, have the program go through confirmations, but here now I do it sort of manually. Okay. And actually, I rotate this down and rotate this a little bit up. Okay, and then I go back here. So this is a very common liquid crystal, turns from the solid, melts into a pneumatic phase at room temperature, exactly room temperature, I think, 25 degrees Celsius, and then becomes isotropic at 35 degrees Celsius. And in between, it's a classical example of a pneumatic liquid crystal. So now let's do some quantum mechanics for this molecule. So I go to the setup dialog, calculations, and I will here, in order to in the interest of saving time, I want to, for this talk, I want to stay not within an hour, but within a minute. Okay, so I will switch here from equilibrium geometry to energy. So actually, I will now do the quantum mechanics for the structure as you see, as I just built it. I will use density functional theory, so something pretty fancy. I will switch to the B3 lib functional, which is sort of the most common one in the world of chemistry. I will do a submit, and here's my, my job has now started, and I can actually look at the job while it's, or let's just, it will take about a minute, so so this is, it will be so quick because I won't try to minimize the energy. I will calculate, the wave function for the structure as is. if I were to minimize the energy, everything would go up by an order of magnitude approximately. Instead of 1 minute, it would take 10 minutes. So here, if I, this should be, will finish. And if I look at the monitor here, I can look, it's running. So here we have 134 electrons in the system. 323 basis functions. So what the program actually does, engineering students relate to that. It diagonalizes 300 by 300 matrices. That's what's really happening behind the curtain. And it should finish in, hopefully in any moment. I could show you in the meantime. I'll show you here actually what is this computer that I'm using. You see my entire screen, so you should. So I'm here using an Intel dual core i7. That chip came out in 2015. So this is a 7-year-old laptop. So it's not bad, but it's not a recent fancy machine. It's sort of something off the shelf, mediocre laptop from with a chip that came out 7 years ago. So there's faster stuff now that you can get now. And I'll go back to there it's finishing. So here actually it took now, it finished. I expected 1 minute. Actually, it took a little bit longer. If I look at the output here, so it took the quantum, the wall clock, the CPU time was 3 minutes, and because I'm running on dual core, the wall clock time was 2 minutes. So it took 2 minutes rather than 1 minute. I had run the example before. It took 1 minute, so I may not. Here, the way I rotated the pentyl group here may not have been very good. Okay, now I have the wave function. Now I can look at various graphical properties, like, for example, the electron density. Molecular visualization was in the title of my presentation. And that's absolutely central for using this program, because Spartan will make it easier than any other program to get to this type of representation. So more surfaces, I select density and no property. Resolution, okay, and it's computing, and there it completed, and I click here. So this is the electron density at a value of 0.002 electrons per atomic unit cubed. I can change actually the this is 99% of the electron density is included here. If I only do 90, let's say 90%. So here, this is a higher ISO value for the electron density. If I do 80%, and you see here, obviously, the two benzene rings. If I do 99.999, 99.99. I didn't want that, so well, it will do 99. Oh, I lost the turn it off. Okay, so this is the electron density. I will now look at calculate here, for example, the dipole moment. If I look at the properties, dipole vector, so you will see that here. I can show so this is the charge distribution of the molecule. I can look sort of old-fashioned, what are the partial charges associated with the atoms? So if I go here to configure electrostatic charge, you'll see here the partial charges for the atoms, but much better, I can calculate a surface which represents the charge distribution in the molecule in a very visual way. So I go to more surfaces, density, potential, that will be fine. And computing, and It should. Here you see the word computing. I'm circling it here. It will switch to completed and any minute completed. There it is. So here is the electron density. Superimposed on that is the electrostatic potential, so which represents electron-rich and electron-poor regions in the molecule. So there's a cyano group here at this end. So this is, basically the free electron pair there is on the nitrogen. So electron-rich. Green is the neutral color. Blue is electron-poor. Green is neutral. So here the pentyl group. We can also change here this representation to the mesh representation, or maybe transparent. So here you can see the pentyl group, electroneutral. Chemists call it hydrophobic. So there's basically no charge to speak of, and here negative charge and positive charge here a little bit here associated with the hydrogens on the benzene rings. I'll turn this off and go to show you one more operation and then go back to the slides. So here I go to configure. So here I chose electrostatic charge. Now let's do, if I can do calculated chemical shift. So this will go to pending. So I can basically now for an NMR spectrum, which now in chemistry, it's the sort of the center of all research. Maybe in material science, not quite as much, but in chemistry, it sure is. I can now switch this from pending to calculated by selecting here the NMR check mark in the calculations dialog and submit. And this was now, I think this will take about 4 minutes to, since the should take a little longer than just the calculating the wave function. So we'll calculate the chemical shifts from scratch by solving the Schrödinger equation. So while I'm waiting for that, I will simply go back to the slides now. Which I have here, and then come back in a minute. So, and full screen. So this is the example this is the slide I don't want to, Yatindra already touched on that, basically the history of wave function. So John Popel, Warren Harry started the company, and he is still, he is now in his 70s, but still going strong and still in charge of the company. So what Yatindra did not quite touch on is that actually Spartan is sort of 2 programs in one. Namely, it's what really comes from wave function, which is the graphical user interface, the whole infrastructure for doing all this stuff. And inside of that is the computational engine for quantum mechanics, not for classical stuff, but for quantum mechanics, which comes from QChem. So the head scientist is Martin Hitt-Gordon from the University of California, Berkeley. There's a huge number of contributors that contribute to the code. Is very similar to what the situation with Gaussian, where there's also an army of people who contribute to it. But in our case, it's one product, one interface. I think you're already getting a sense of how easy it is to do things. There's a little bit of a learning curve, but then a few mouse clicks will get you an incredible amount of information. Here then I'll check whether my NMR calculation has finished. Here's sort of the mission statement for the company, wave function. What sets wave function apart from other companies that also are offering quantum codes or academic quantum codes. So we have been truly on a mission for 30 years of making molecular modeling easy and accessible, so that it can be used not for highly trained but just by highly trained experts, but by bench scientists, chemists, whether it's synthetic chemists or material scientists or chemical engineers or petroleum engineers, people who are in the lab, who are not, full-time computational chemists. We are always pushing very hard for standard methods. Uh, um, Huge problem with applying computational chemistry methods is, like, there's a zoo of methods in the literature, and as the innocent user, you don't know what to, what should I use. We are doing a lot of hand holding there, sort of pushing people towards picking things from a fairly small set of standard methods. 3D molecular visualization is a center part of our software. You already got a sense for that. And education is also something we care about a lot. So this slide, I think Yatindra already had it. I will here sort of show it now, highlighting a little bit, but from a material science perspective, what would be, of really of interest. Building, creating your model either with 2D or 3D, doing the quantum chemistry, calculating structure, calculating spectra. One is running right now, so for this NMR, and handling of lists, which I will touch on in a little while. Molecular mechanics, which is sort of, you always step prior to quantum mechanics. And then I should point out, material scientists typically are very aware of the Cambridge crystallographic database, at least if they deal with, at least occasionally, with organic molecules, which is now over, I think, 1.4 million structures. This is a separate license, but many universities have that license. So Spartan and Cambridge, the CCD database sort of seamlessly interface. I should point out, though, what you extract from that is not the periodically replicated structure, because Spartan sort of ignores that, but the molecular structure as it's contained in the Cambridge database. So this is what flows into Spartan. It's not the space group of that was determined. And I will go close this and see here. So it has completed while I was looking at my slides. So here you now see these are the calculated chemical shifts for this liquid crystal. And if I want to look at the spectrum, there's the from the conference system, the icon bar is a little bit in my way. Probably you don't see that, but so here's the icon for spectra, and in the lower here, so calculated NMR spectrum. I will close this. So here's for I can, if I select here, you see here up on the here you see the chemical shift. So for these two nuclei, for this nuclei, so if I scroll through here, you can see it starts lighting up where which hydrogen nuclei affected. So this is for the proton spectrum. These days in chemistry, actually, mostly what's of interest is the calculated carbon-13 spectrum. That has very much changed over the last 10, 20 years. Now everyone does carbon-13 because the technology has advanced so much. Here the same thing, so where you can see here where the chemical shifts for the nuclei that it is associated with. If you Yatindra had mentioned that you can calculate, compare this with experimental. No, I think he was a little bit too generous by saying, oh, it will always exactly reproduce the experiment. No, well, theory and computational chemistry is hard, so we are doing very well in that department, but it varies from case to case. Now theory has advanced to the point where you can make predictions, successful predictions, and then verified experimentally. So it's a far cry from the past where you have huge error bars. But there's, it will vary from case to case. So it depends on how size of the base is set, and how hard you try. I mean, if you more intricate calculation will get better results, as one can imagine. Okay, so that's I will close this here and now show you quickly here I mentioned, and I will first turn. There's so much stuff here on the screen. I will turn off the labels, models, labels. So, okay, I will turn off the the dipole moment arrow. And I will calculate a few more surfaces, and then I will touch on this whole issue of looking at more than this is one particular liquid crystal and comparing a family of liquid crystals. We'll try that in about 10 minutes. But first, more sort of very graphical information. First of all, so we calculate the wave function, and obviously, so we have molecular orbitals. It's molecular orbital theory that we are using. So if I select here, if I click on orbital energies, here on the left side, it immediately shows me what are the orbitals from the HOMO down, the last another 10, I think 10 down here and 4 up there or something. But in principle, they are all known, of course. You can request all of them. So if I click here simply on HOMO, so I will get a representation. I put this in a wire style here of the highest occupied molecular orbital for this liquid crystal. Here, the ones below, so and so on. Here for the LUMO. So what I get, molecular orbital theory, I will get a HOMO-LUMO gap here. So that sort of maps on, the band gap in a band structure calculation. It's just we don't do a band structure calculation. It's a HOMO-LUMO gap in a molecular chemistry calculation, molecular quantum chemistry calculation. I'll turn this off and go to try to look at a few more surfaces. That's sort of if you're here in the setup dialog, these are the two central ones. I mean, the one is the edit, which is building, or build. It's the build dialog, building, edit, build, edit. And then there's setup, calculations. They declare, what do I want? Do I want classical? Do I want quantum? If I want quantum, do I want DFT, or do I want something faster, or something even fancier than DFT, which is in the program, but not actually, I'll quickly divert to that. So while I'm on it, so here's the calculations dialog. So I can go these are the levels of theory I can use. Molecular mechanics, that's classical. So this is instantaneous. Some seconds. Some semi-empirical is old-fashioned molecular orbital theory where with lots and lots and lots of parameters in it. It's still useful to get trial wave functions to go further up, but it's sort of a little bit obsolete in terms of, as the final result. Hartree-Fock is sort of a workhorse for molecular orbital theory, has been superseded in the world of chemistry largely by density functional theory, though, because DFT has become so good and is now that's what everyone uses. So Miller-Placid here, if you go further down, now it gets really expensive. Miller-Placid wave function based correlated, these things all run very slowly, and this is basically material scientists won't care about this anymore because these things you get incredibly expensive. These are, theoretical chemists who are interested in tiny molecules, calculating them to incredible precision. They will use these methods. There are plenty of users who want to do this, so we cater to them too, but it's not for a scientist in the lab. It's of limited interest. So the DFT, so here you have various functionals. So as I had mentioned on the slide that standardization is a wave function real theme of all the work we do. So you see here, this is what we're doing. So there are these 5 methods, and actually really what we are pushing is the first 3 only. B3 lib is, if you're not a chemist, you may not be familiar with it, but it's still the most widely used in chemistry in the world. This is the one that is the default in the program. Actually, if you it will default to this. It's a mouthful, Omega B97XD. It's sort of the next generation after B3 Lip. It's better, but it's also a factor of 2 more expensive, 2 to 3. It seems to be because computers get faster, so we now made it the default. If you want a little more speed and still good, B3Lip is the way to go. And here's the basis set. So this is the the zoo of acronyms that gave computation chemistry in its early days such a bad name, because if you are not do this full time, you feel like drowning in these acronyms. But so this is we again, rather than the true number of basis sets available, is gazillion. So we push people towards the ones you see in this short list. If you want to go further, you can do it. It's the same here for DFT. You want other functionals. Surprisingly, many people always ask for it. Here are all the options you have. Okay. It's like global hybrid meta generalized gradient approximation. So I'm not an expert for all these things. So some TPSSD3, I don't even know what the acronym stands for. It's all available if you want to, but we are not advertising it prominently, because most people want just a standard method. So the standard method would be what's in this short list. Before I close this dialogue here, energy is for the given structure. Equilibrium geometry will minimize the structure, by using a minimizer to find a minimum energy structure. Transition state is going uphill. This is relevant for chemical reactions. Conformers is something that chemists for flexible molecules care about, a huge deal. I don't think I will have time to talk about that today. So energy profiles for chemical reactions. NMR spectrum is a particular sort of its own dialogue, which calculates really fancy NMR spectrum, not just what I did earlier, but it will calculate a Boltzmann average of different conformations. Very, very, very complex for extremely high quality NMR calculations. And then here you have check marks here for the various spectra. NMR is the one I chose earlier. UV vis, Raman, IR, I will mention briefly later without calculating it. You have to calculate what is the charge of your system, because that's all that goes into the calculation is what are the nuclei and how many electrons there are there. So you have to declare whether it's neutral, cation, anion, or so on. And then the number of unpaired electrons, that's the spin multiplicity. That's something you have to declare. The program cannot decide that for you. So you have to, usually it's 0, closed shell, open shell, radicals, so would require here, a different number. Okay, that's enough of this dialogue. And I'll go here. So building, calculating, and then looking at result at the graphical properties, graphical models. That's the surfaces dialogue, which is here. I just deleted it. So I did 2 earlier. Now I will look at a little more what's there. So you can also calculate explicitly molecular orbitals, HOMO -17 or something like that. I can calculate the electrostatic potential itself. And if I do this here quickly for this molecule, yeah, that was there immediately. So here is actually, it shows you the lone pair here, basically on the nitro group here. Cyano group. I can calculate, I have available, let's do here also the ionization potential, so which will give a graphical representation of where computing completed there, where the molecule will be most likely to get ionized. Now there I chose a value 20 eV. Let me do a different value 20. No, ionization potential. It can all be customized, so fixed. Rather than 20, I will use only 10. Enter. And computing 10 and completed. There you see here, the ionization won't happen, on the pentyl group here hanging off on this side. It will happen on this side of the molecule. Then I'll go here to the final one, which would be slice. So I will do a slice of the electron density and select completed. It's immediately there. And select this here. And actually go to properties and change this from contours to solid. So what I'm now looking at is I'm scanning basically through. Then I will select this. I'm here scanning through the electron, in the slides, looking at the cross section of the electron density as I traverse through the molecule. So it's a very, very, very visual representation, of the electron distribution in the molecule, and you can use this for all kinds of things. So I think that another one, which I won't show an example for that, because for that I would need a radical, would be here as the property spin density, which is not shown in the dialog here, because the program recognized that this is a closed shell system. There are no unpaired electrons. If there were unpaired electrons, it would offer me here the option also to calculate isosurfaces for the spin density. Okay, so that's the story with graphical representation, calculating spectra. You saw that. You saw one example, NMR. So also exists for IR, UV vis, and Raman. Know something a little bit about looking at more than one liquid crystal at a time, and in order so that it won't immediately always calculate these surfaces, I will delete all of them, because if I will now add more molecules to my list. Right now my list is 1. Now I will create a list of 3. And I can also create a list of 300 if I want to, and I'm patient enough to run the calculation. So here's I will go to the Spartan spreadsheet, which is here. So here's my molecule 1, and I will copy that and paste the molecule, and paste it again, paste the molecule. Let's do 4, paste. Okay, paste molecule. Now I choose this one here and we'll modify it. So let's say rather than a cyano group here, I will put a hydroxyl group, just something arbitrary. So I will go to edit and I will chop off here this and put an OH on there. And then I will go to the next one and also chop off here and put a fluorine on there. And then I will go here and just completely arbitrary add a methyl group, or make the chain here, the pentyl chain, shorter. Let's do that. So I'll chop off here from pentyl. I will go to ethyl. Okay, so just 2 atoms there. So I just created a list of 4. I can uncouple these. So there's no other software that has the tools to do this type of thing. I should zoom out a little bit. So, I mean, this is an arbitrary example. So you have 4 different structures. So I want to compare the properties for these 4 different structures. So I can, they're all in this, in this, if you go to the spreadsheet, there are the 4 listed. So what it's just one additional check mark in the calculations dialog to get the data for all of them at once. And obviously we'll run longer because there are 4 rather than 1. So I will go to set up calculations, and I will set here, I'm circling it here at the bottom, global calculations. I will set the check mark global. And in order to make this, the one was for previously 2 minutes, so I don't want to run it for 8 minutes. I will go to quickly here to use Hartree Fock, step down from DFT, go to something a little bit cheaper. Hartree Fock, and I will remove the NMR check mark and do submit. And now it's running. I have a dual core machine, so it will run 2 of these at a time, on each core. So I can always, with the monitor, I can watch that. So here this was the first one in the list, and the second one in the list. So which was I think, so this one and that one are now running at the same time. So 4 of 4 remaining because it still hasn't finished. 1. So let's be patient. Hopefully, maybe I should have stuck to 3. So I got carried away doing 4 of them. I also did what I missed. I should have minimized first classically in order to get a better initial structure. That was a mistake I made. So then it would all run faster. 1 minute. It's not even faster than DFT, which is okay. They had finished. So 1 minute, yeah. So quantum calculation time at Hartree Fock was 1 minute. So half of DFT. So 2 of 4 remaining. Now it will do so it is done with the top 2 here. Now it's doing the bottom 2. And so we are each one, 130 electrons. So we are doing 4 calculations of 130 electrons each. So I mean, this is sort of astronomical compared to the early days of quantum calculations on an off-the-shelf laptop. So and we are at 50 seconds. So these will finish also in 1 minute. So that. I don't want to go back to the slides until it finishes. So. And there we go. 1 remaining. There's 1, or the last one, and it completed. So, okay. So now I have 4 times. So I can go to the spreadsheet. For example, if I want to add here, what is the dipole moment? So of these 4. So this one here has a dipole moment of 6 dBi. This one here has a dipole moment of only 1.9 dBi, a lot smaller. Okay. If I do here and the other ones here are, some other value. I want to look at the HOMO-LUMO, the energy of the HOMO. So at an EV, and you could calculate here also, do the same for the LUMO at the LUMO energy. And you can, now there's a syntax here, just like an Excel spreadsheet, where you can calculate the gap between the two, so the equivalent of the band gap and the band structure calculations. So the wave function, just the graphical models, again, there's just all I need is the global surfaces check mark in order to, I will do here low, you can choose the resolution of these surfaces. So either low if you go up to ultra, very, 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 very beautiful pictures, but will run a long time. So low is really fast. So it will do all four at once because my global check mark is set, and I will get the submit. Oh, it's already finished. So no, it's computing after I submitted it. So it did not immediately calculate it again because I had not. I had removed them from the list. So here, are the two for these, and here are the other two. So that was 4 different surfaces, all in, with just by including the global check mark and in the dialog that I had to go through in order to get the data. So this provides you with an idea of how you operate with the program. The inorganic chemistry is sort of building. This is still it's an organic molecule, this liquid crystal. But if you want to really venture out to true inorganic chemistry, that's not easily done by selecting the inorganic panel, and I can build iron tetra. Yeah, I didn't pay attention now to the let me here tetrachlor here iron tetra or chloride bromide or something. So it's I can here, if I do the the entire periodic table, like platinum here, and so it's the periodic table, will opens it up towards inorganic chemistry. So that I will go back to my slides and say a few more words here about what you just saw. So commentary. So the relative computational cost, and let me see the Ring Central screen. Okay, we are 1 hour 5 minutes in. Okay, so here, oops, and I wanted to go to PowerPoint. So and full screen. So the relative computational cost, I sort of touched on that, is for semi-empirical is incredibly fast, is still good for getting good trial wave functions. It will speed up, using a more accurate method. Hartree-Fock, I just used this for the second example for the list. DFT here. The B3 still the most popular functional, and the one we are pushing, which is more expensive but more accurate. MP2 is the stuff which I belittled earlier by saying this is still cheap. 10. It gets. You do even fancier stuff. It gets. It gets you to a factor of 100 and 1,000, and not very interesting for people who actually deal with real, molecules other than theoretical chemistry molecules, which are tiny. So I'll go to the next slide here to again what can be calculated. Obviously the ground state, you can get easily the first excited state, with effort also higher excited states by a few mouse clicks. Transition states, if you're interested in chemical reactions. Molecular flexibility is there's a ton of tools and support in the program for dealing with conformational degrees of freedom. Atomic charges, I showed that on one model. So electrostatic charges is the one we recommend, which were obtained by fitting to the electrostatic potential on an isosurface around the molecule. Molecular charges are available, so people always ask about that. They are old-fashioned, but people still want them. Natural charges, another also available. So this here is the centerpiece of Spartan, namely that isosurfaces you will extract with just a few mouse clicks as opposed to an intricate procedure. I mean, other uh, uh, um, graphical user interfaces will also give you that information eventually, but you have to jump through lots of hoops to get to that. So here you get, you saw examples of these things. You get them with just by a few mouse clicks after, an afternoon of working through a tutorial. Spectra, so I will only sort of touch on that. So NMR spectra are calculated by the program. What actually comes from real theory is the chemical shifts. The coupling constants can also be calculated from scratch, but it's very costly, actually. And the spectrum that I showed, for example, it used the default. The splitting of the peaks came from the Coupler's equation. It's an empirical algorithm. It does not come from first principles. So that's a full disclosure. It can be done, but it's very costly even now. Boltzmann averaging, I had mentioned that, is sort of a very fancy way of calculating NMR spectra that's very relevant in organic chemistry for natural products in particular. Other lists of chemical shifts for other nuclei, which are often of interest in material science, are also available in the conventional output. They are not graphically represented. You have to go to the output. UV-Vis spectra can be calculated with either Hartree-Fock or now these days with density functional theory, time-dependent density functional theory. The default is to include 6 excited states, so they can all be all the stuff, NMR as well as UV-Vis, can be compared with experiment with a mouse click for those compounds that are contained in public databases. For UV-Vis, it's a NIST database at the National Institute of Standards in Washington. For NMR, it's a database at the University of Cologne in Germany. For IR, it's again NIST in Washington. So IR, Raman, can be calculated in just the analogously. So the Yatindra had touched on that, and I want to emphasize that too. So because it's a huge advantage over, I have not seen any other program that actually does that much hand-holding and takes you with an afternoon of quality time. Let's say an hour, for each of these, or a couple of hours for each of these squares here that I've highlighted. It will take you from zero, from never having done anything like that, to being a power user just by an afternoon of quality time to work through these tutorials. These are PDF files which of these examples, all these things sound very organic. So even if you're not an organic chemist, you will just forget about the nomenclature, just follow the instructions. So they take you step by step, explain by working through examples, familiarize the user, with the power of the program. And you'll be amazed by working through these that you'll go from, from not knowing anything to getting very powerful spreadsheets full of data for various compounds and so on. In the world of molecular chemistry. So not, again, it's not a band structure program. It won't deal with, periodically replicated structures. Here's also, how to use Cambridge. There's a tutorial for that. I want to point out that, which had Yatindra touched on, but I want to say it a little bit more prominently. Spartan is the program that I've been using, which is now on Spartan 20. The Spartan 22 iteration is in the works. Hopefully will come out before the end of 2022. It's the next iteration. So that's the flagship program, which is used all over the world. So available also for Linux, not only Windows, obviously of interest in India, Macintosh less in India. It's the program which has all the bells and whistles. Spartan Student is a cut down version of Spartan in order to introduce graduate students to real modern computational chemistry. So it has the limitation is it will allow you up to 30 DFT up to 30 atoms in the molecule. It won't do 100 atoms research molecules. So the program is very very much cheaper, and it's pushed towards student use. So it's an education focused program that is not available for Linux. So that is the two levels of Spartan. Spartan, it's called. I think we took off now for Spartan 20 already. It has the moniker Parallel Suite. It used to have the moniker Parallel Suite. This is now sort of becoming such routine that we've taken it off. So it's fully parallelized, and it's like we'll really take advantage of all that now so many laptops and desktops run now in parallel mode. So it really takes advantage of that. And the last slide here is the Spartan brochure. I shared these slides this morning with Yatindra. I shared an earlier version also with the host today. I think you can click on the link. It will go to the Spartan brochure and show you the all the details in the. Let's see. Can we? See. So automated conformational analysis, automated NMR for flexible molecules, DP4 support that has something to do with I forget even what DP4 stands for, basically with natural products, not very much, not of interest for material science. Coupling constants, there's constant progress. 2D sketches from 3D structures. Now we go both ways. You can take a 3D structures, go back to 2D. Here, all the gazillion of different functionals, even though I stick by my earlier point is we encourage people to use a small subset of these, which where we have a lot of experience. So but there's people want I want this, so this particular one, so it's available. From the different basis sets here, also not only the Popel basis sets, but Dunning basis sets and Ulrich's Huygens basis sets. The user interface, lots and lots of 30 years of work on this, many, probably 100 man, or more than 100 man years of work that went into that. Hundreds of man years. So different tasks that the program can do: calculates heats of formation, calculate gas phase, equilibrium transition set geometries, calculate activation energies for chemical processes, computational methods. A long list, properties and QSAR descriptors. So QSAR also relevant for material science, which is calculating from solvent accessible areas and stuff like that. Spectra, additional features, multi-core parallel processing for Hartree-Fock, DFT, RIMP2, and thermochemical recipes. Automatic processing of groups of molecules, Automatic use of molecular symmetry, yes, of course. Databases, there's a built-in database of 300,000 molecules, which you get access to. It's a 20 gigabyte file that you download separate from the program, which contains 300,000 organic, mostly organic or organometallic molecules, which have been, where the wave function has been pre-calculated. Useful, for to get starting points. Often, if you make new stuff in the lab, so it won't be new stuff won't be in it because no one has seen it before, but it's a good reference. Enhanced parallel performance, chemical shift labels. Okay, and here's the price list for the US. So, which and the specifications for Windows. So we only support 64-bit anymore. So 32-bit, sorry, there's no support for that anymore. The Windows 8 and up, including Windows 11, of course. Linux, these distributions of Linux. I'm not a Linux user personally, so I can only acknowledge that these are the distribution it works with. The amount of memory, it all depends. The more the better, but it's not like if you don't want to run huge systems, it's not like you don't need huge amounts of memory. Graphics card, the graphics will if I go back here and go back here to my example. So if I go to turn off my surfaces and put it on space filling. So if I have these, and I can rotate all of them at once too. So here they are now. About how many atoms are there on the screen? I can. This molecular weight. Each of these is 250. So it's about total of 1,000. They are actually. I can look at. Let's see. Properties. So molecular formula. So they are about 40 in each. So there are 160 atoms here on the screen. So 160 atoms. So once I get to 1,000 atoms, let's say, then this will rotating the model like that will become very, very slow if the graphics card is poor. So this is the main effect. Okay? Poor graphics card, small molecule will handle it well, especially only one, but big and biochemists, for example, they have huge models often, and then in space filling, I use here. This is a cheap model style, ball and wire. That's cheap, or tube style. That's no problem. But space filling. I mean, the computer draws these, through individual triangles, gazillion individual triangles that make these smooth surfaces, and that gets very slow if the graphics card is poor. So, nicer graphics card, you'll get. Mine is just the Intel on the chip graphics. It's not a special NVIDIA graphics card or anything like that. It's just the graphics card that this is a Lenovo laptop. So that it came with. So I deliberately wanted to have something that everyone uses, not something a fancy developer's machine. So this is an application oriented machine. Okay, that's I'm it's 11:20 your time. I wonder if Yatindra could step in and see whether we can do. Is it possible to do a Q&A session or to see what?
So obviously we can go for the Q&A. If participants have any questions or they want to ask some queries, definitely we can take Q&A. So please, if you want to ask any questions, you can come to the mic and ask to Dr. Jagan. Thank you.
It is time for question and answer session. I request you to raise some questions. Whatever you have learned, you have some queries, even though it is something new for you. But if there are queries also, you may ask, and then sir will resolve it. But you have to come here so that he can listen to you what you have asked. Come here. Any question? Raise your hand. I may come to you, and or either you come here and ask. So let me start. Sir, I have one doubt. Is
Uh-huh.
I am myself Satyapal, SB Singh. Sir,
Uh-huh.
let me start with putting one question before you, so that these people get some courage to ask.
Okay.
They
Okay.
are hesitant, right, sir? So the thing is that what is the maximum number of atoms with which we can create a molecule or macromolecule using Spartan, and what kind of
Okay.
computation resources are required? Suppose if it's
Yes.
100 atoms and so on, or even
Yeah,
larger
yeah,
ones.
yeah, yeah.
So
Very,
how
very
much?
relevant questions. Yes, especially uh, people who are completely new to using methods like that often have sort of no. I mean, they have no background, so it's very completely fair to wonder about that. It's like it's all seems to um, be the same. So, yeah, Tinder already had on one slide. It's and I think I had it also on one, which is the magic number for calculating organic molecules was 500 atomic mass units. So, which includes this comes from these are most all small molecule pharmaceutical drugs on the world market are basically fall within that, other than biomolecules. Um, so the same, this also, once include all the elements from the periodic table, it would still be the same. So you are talking about, hundreds of electrons. So the molecule, this liquid crystal I used was 250 AMU, 5 PCB, 5 CB, cyanopentyl biphenyl. So this was 130 electrons. So you get twice that would be 260 electrons. So let's say, well, once and things you can go, can make the model as big as you want. Things will just get incredibly slow, and the calculation will run forever. That's the issue. Uh, if you stick just to a classical view, to the molecular mechanics option in the calculations dialog, so classical, then there are no limitations whatsoever, basically, because this is quick. You can have 5,000 atoms, and we'll handle that. But for, if you want to do quantum mechanics with it, which is, this is what you're really after, why should you use otherwise such a fancy tool, is to so a few hundred electrons are now doable on a time scale of uh, hours, so from tens of minutes to a few hours on an off-the-shelf laptop as I am using. Okay, so you put it on a fancy, in a supercomputer. It will run, even that will run for 1 minute. So I'm or a highly parallelized, I don't know, a Linux machine, with who knows how many nodes. I mean, those things might do wonders. So I don't personally use these, and so I think more in terms of what can you do, with your laptop or the desktop in your lab, so your personal desktop. And so it's a few hundred electrons. That's doable. If you think about it, this 2022, that this is no possible is just mind-boggling. Hundreds of electrons. Solving the Schrödinger equation from scratch with uh, without. DFT does contain also parameters. It's not. It's first principles in quotes, but it's not semi-empirical really. It's like it's close to first principles, and we can now do this, on on an off-the-shelf laptop. I mean, it's mind-boggling. So yeah, that's you don't need. It doesn't have to be the nicer the machine, the further you can go. That's just same as with a car. The bigger the engine, the faster you can go. So the smaller the
So,
engine, so the the less
right,
you can
right,
do.
sir.
Okay.
Yes. And some questions from you. I have one more question I shall ask later, but first you ask because you are the participants, you are the main learners. You have any question? What can we do? What type of things can be done? This is also a question. You may raise simple questions because we assume that you don't know anything about because main of the most of you are the pursuing your MSc project or have started your PhD work. So we don't expect that you know the advanced things. Just raise your whatever queries come into your mind. Just raise. To make it a workful event, your both way interaction is necessary. Both way participation is necessary. So you have just listened it carefully. Just comment on something. So, sir, again, let me ask one more question.
Okay.
Meantime, they may think one more question that I have been doing classical simulation like Monte
Hmm.
Carlo simulation and MD simulation for last 15 years.
Hmm.
So 3 4 years back, I have started this quantum simulation because
Hmm.
the mix up of those things will give a better molecular insight. Thinking of this, I have started. So one of my PhD scholar is working on that. She is going to complete by the end of this year.
Hmm.
So the problem which was coming over there was that when we select different basis sets, functional and basis sets, a
Hmm.
combination of that is very key important thing means uh, for metals some other you need some other functional and functionals and for inorganic molecules some other functional works better for higher atomic number atoms some other
Yes.
functional. Why all these variation comes into? Why don't you people discover a single which work for all
Yes.
kind of atoms and
Yeah.
so that
Yeah.
because
I
meantime our program is broken, it stops
yes.
working, right?
Okay.
Yes, please, sir.
So yeah, I agree. I'm completely with you. So all I can say is that Warren Harry, who started Wave Function, and the company has been doing more, trying to do more about this than anyone else. Most, I mean, other programs. I mean, in the academic community, I mean, everyone is, in order to show that you're innovative, you want to comes up with something new. So there's a new functional every few weeks. So the list grows and grows and grows and grows. So what we are, I mean, all I can say is that if you look at the default options in the wave function menus, look at the documentation. Actually, I think Yatindra had pointed it out in the there's in the if you go to the help menu in the upper right corner of the program, there are topics addressed, and there are sort of fact questions and stuff like that, where you'll see pointers to what you should do. That's we are trying to not to I mean. But all the other software you can find, it's like, so it's up to you. You can use whatever you want. We are actually trying, we don't have the perfect answer. I mean, it's extremely complex, but yes, I completely agree. It's like a disease, it's like we don't need another 500 functionals. So it's we,
Uh,
uh,
yeah, of course, from our perception, it should be one and universal one which solve all the
yes,
problems. And
yes,
of course,
yes, yes.
Professor Jargan has made it the software spartan means density functional theory and other things, quantum simulation tool. These are quite useful in the terms. These are user friendly. You have
Yes.
seen that pictorial pictures, images are there. You can just pick and place, and then you can start by clicking using the mouse. So it starts running and it gives data. You have the Excel sheet, all these things. The main user friendly interface, window interface, everyone knows. So this is the
Yes.
main feature and most beautiful feature of this software, which I have just used for last 1 or 2 years.
Yeah.
So of course the trial license, right? And I have asked for written for the software in some project work. I am waiting for that. So some questions from your side. We shall welcome questions from students because we are targeting students. We want to teach them. We want to train them. I will be happy if you raise 1 or 2 questions. Where is Archana? You call him. So call her. So any question? केमिस्ट्री के लोग बैठे हैं बताओ भाई. You have some doubt? Yes. Come here. Sir, थोड़ा encourage करना. We have to encourage our students. They are a bit hesitant. One person is coming.
Right.
Yes. Please.
Good afternoon, sir. My name is Satyam Singh. I am working on the graphene COF. So these masses are very high. So it is capable to do in this software for DFT calculation. If we making
Yeah.
a COF, so can we easily calculate the DFT of the COF or any?
Yeah, so you won't be able to you cannot calculate the periodically replicated system. What you will do is for the I mean the graphene layer is easily modeled. You will have to saturate the edges, with hydrogen atoms in order to make it, a molecular entity which does not have free valences. So then it becomes then at that moment you are in the world of molecular chemistry, and now everything will just work just fine. So that's actually graphene is this it's a 2D system that's you can actually go. I mean, I said a few hundred electrons you can handle. I mean, you can go kind of rather extended layer of it. So, but you have to always, if you do more clusters, of anything that's in reality periodically replicated, you will have to worry about the free valences at the edges. If you don't worry about that, then you get it's all dominated by edge effects. So the routine trick, is that put hydrogens on it. So.
Okay, thank you, sir.
The little bit kindly allow me to elaborate. When you are working with some sheets like graphene is a layer, so there are end effects and so on. Where to stop it? So because usually these are infinite systems, even though it's thickness in one layer, say monolayer or so, but it's one of the dimension, two of the dimension are maybe of infinite size relatively. So it means larger and larger number of atoms should be there, means in that layer. So periodic boundary condition offers solution to this problem in classical simulation. What is there inside this quantum simulation to come off get rid of this end boundary problem?
Uh, Spartan it has never been an emphasis of Professor Harry. I mean, who has spent his life, creating this program, and it's something. It's because it was not. I mean, it's used for material science applications, but this was not the genesis of the program. So we have not been. The natural way of dealing, with periodic boundary conditions, periodically replicated systems, is to use a plane wave basis set. So that's why you complete set of tools really for material science problems really requires 3 programs. I mean, it requires Spartan that you just saw. It requires a band structure program, CASTEP or VASP, for example. VASP from Austria is very popular now. I think it even has this academic licenses, which are less than the commercial licenses, and a classical program that you have been using for a long time, Monte Carlo / molecular dynamics program. So, which also Spartan doesn't do. Spartan is so I mean, you've seen the strengths of Spartan, so and which I think will stand out compared to any comparable program, but Spartan won't do anything. That's the answer. So
So the
it
answer
won't, it
is
won't do
means
everything. Won't do everything. I mean,
so
won't
the
do everything.
periodic bonding condition, in fact, comes when the molecules are bigger one, or there is some molecular motion, translation or some motion, in which you need the images for shortest distance
Yes,
calculation.
yes,
Otherwise,
yes,
we don't need it at all.
yes,
So
yes, yes, yes,
that
yes.
option is available at this hour
Yeah,
in 20
yeah, well,
Spartan.
with at the quantum level, it's a lot harder, than a classical simulation, than classical MD, classical Monte Carlo. So it can be done. I mean, there are programs that do that, but I don't think physicists even use them. I mean, they will use plain wave codes, to
So
to deal with
that
it.
comes only into particular cases, sir. I agree. Yeah,
Yeah, yeah,
and
yeah, that's
otherwise
true.
it has no
Yeah,
relevance to the most of the simulation work.
yeah.
Archana, would you like to ask some question? Yes, please come here.
Good morning, sir.
Hello.
Sir, I have a question.
Yes.
Sir, I have plotted one electrostatic potential of a liquid crystal molecule.
Mm-hmm.
Sir, I obtained open surface electrostatic potential surface. Sir, my question is, it is possible, it is right that I am getting open surface electric open electric potential surface or not?
What do you mean by open? It's maybe I'll
Sir, she is doing PhD under me. I am supervising. Open potential surface means it doesn't appear like closed one, means like sphere is a closed surface. So it is some planar surfaces are
okay,
coming.
okay,
Sir
okay,
has shown.
okay.
Sir has shown in
Yeah.
detail. Yes,
Okay.
it is right. Sir,
So
please
I
comment on
think
that.
you can see the program again, can't you? So I'll turn this one here to tube style, and I will go to properties and select a surface and turn on the clipping. So is that what you're talking about by open?
Sir, please explain why it is open.
Yeah, because
Yes, sir.
it's
Yes, sir.
no, it did. I mean, the program did it ad hoc. Some you can I selected so it's one mouse click in the program. I mean, it's typical, again, the power of Spartan. So I went to the display dialog, I selected properties, then I click on the surface. By default, the properties dialog is for the molecule. I select the surface. Now here I have the surface dialog, and now here you see the option clipping. So here's one plane, here's another plane, and here's the third plane. So I mean, it's for 3 different directions. I'm not sure if you can declare it for arbitrary directions. So I mean, you just try out which one is most useful. So this feature has actually been in the program only since Spartan 18 or something like that. It hasn't been there forever. So it was sort of a hidden developer option. Now it's available to everyone. So it's one mouse click. If that is what you mean by open surface.
Okay, sir. Thank you, sir. I've got my answer. Thank you, sir.
Okay, sure.
Okay.
She has got it. Means plane means just like a sheet of plane of paper. So those surfaces are not looking like that, curling over and then bounding. Again curling over and coming and joining together. So it was like planar sheet, a paraboloid or something, but open from one side. Something was like that. So maybe perhaps in the setting also, she may search it out and then different kind of views may appear. So the question is that whether it must be necessarily closed, sir. Closed in the closed surface must be necessarily closed theoretically.
No, I mean this is just. I mean the program is now only show. I mean the density, the electron density surface, of course, is there. I mean it's just now it only shows part of it. That's. I mean there's nothing deeply physical going on. I mean this is just
Right.
it's just a different visualization style.
View of that. Right.
Yeah. So
Okay,
that's.
sir. Thank you.
So that's not a. It's not. It hasn't. The molecule hasn't changed, or the
Right. Right. So this is what you have shown. Huh? This
yeah,
kind of
yeah.
surface appears. So she was little bit worried. Then I said that of course I am also new. Let us search the literature and if necessary we shall ask some expert. So I
Yeah.
hope that she has gotten the answer. Right. Thank you, sir.
Okay.
Some more questions? So, yes. Yes, please come here. Mr. Saurabh is going to ask. He is doing his MSc project, master's project. Sir.
Okay.
Using density functional theories, we usually do for heavy nuclei, we usually perform LAN, LY, 2DZ, that simulation. But can't we do it with other program? Because I have read some paper where it was saying that it is invalid to use that configuration, that it doesn't give a proper result.
What method did you use?
So I was currently working on Gaussian, where I was working with silver atoms. So in that, when I was using the configuration B3LYP, then it was not giving me appropriate results. So I
Yeah,
tried to do
that's
it with, yes, sir.
yeah,
So yes,
that
sir,
doesn't
yes, sir.
surprise me. It's like B3-lip is the workhorse functional, for organic molecules. Now, silver is like that's. I mean, some of the previous remarks, touched on that. It is once you get, to transition metals, things do get more complicated, and you will be. I mean, this now becomes a little bit of an art form where where you have to see what has worked for people before. The B3-lip will do poorly on on silver, and does not surprise me. So I wonder how whether this omega B97XD, which is the new default in Spartan, would do. If that is not an improvement either, then yeah, that's you will have to dig deeper, and eventually you will have to try out a little more of these these all these other hopefully not you won't have to try out 100 different functionals, but you will have to look around a little bit what works and what doesn't work. It's you are there at the frontier of of using these methods, so it's you mentioned it's studying the literature and trying to be on top of that requires work and experience, and I can't advise you on a particular problem. There's no substitute for doing your own digging. So
Sir, I was working with that biomolecules in correspondence with that silver atom. So can you guide me that which configuration should I take that it will give me an appropriate result? Because I was
well, I
doing,
mean, so yeah, the first step is try the new default in Spartan, omega B97XD. So which is, Warren Harry has run. We have an in-house Unix cluster, and has run spent enormous amount of computing time, and it accumulated huge tables of data for all kinds of stuff. And sort of the upshot was this is the best we can do at this point in time. So doesn't mean it will still be the best in 2030, but it's the best we can do now without spending, without going completely overboard in terms of computation time. I mean, it's some, uh, um, there's, by going to advanced correlated methods, with you can always get a better result, but, the computation time becomes astronomical, I mean, it's because the scaling behavior of these really fancy methods is horrible. It's the power of 5 or often the power of 7. Now imagine that, power of 7. So you double the size of the system, and it's 2 to the 7th in computation time. I mean, that's a complete killer. So it's so DFT is always there, it's the one thing where you won't drown in computation time. And but this is not, I think not for organic, carbon, hydrogen, nitrogen, oxygen, which is what phosphorus and sulfur. This is all they, organic chemists care about. That has matured a lot. So, but for transition metals and all the other stuff. So you are a pioneer, establishing that. You're no longer the only one doing this, but so you are, try to consult other experts, make yourself into an expert, and contribute to the literature, and we will make progress on this.
Okay, sir. Thank you, sir.
So some more questions from the student side? No, sir. They are new to this area, and few are engaged in. They have raised their questions. So there was one more question from our side, since our group, some of our group members are working. Sir, some scaling factor is also required to compare means these DFT simulation data. Suppose someone gets some spectra like IR, NMR, and UV, and so on. So some scaling factors are required somewhere. We see that the values are different to correlate with the experiment.
And they are built into the program. Yes, that's always this is why I'm, sometimes there should be a little bit disclaimer in what you're offering. And I mean, it is all first principles compared to all the so much other stuff, but sometimes there's a little magic factor, very famous for actually I think for Hartree-Fock and DFT is understood. It has to do with the shape of the potential well for the at the minimum energy configuration. And so in order to reproduce the experimental data, there's a magic correction factor. It's about 10%, in order, which will improve agreement with the experiment dramatically. So yes, that makes it no longer a true ab initio method. Admit it, no doubt about it. This is the best we can do. So I mean, eventually there are approximations. There's a harmonic approximation goes into the calculation of the R spectrum. There are, even though it's first principles, there are a bunch of approximations being made along the way that people don't talk about them, but they are there, and we eventually deal with that by having fudge. You can call it a fudge factor, but and then it becomes so it's sort of it's first principles in with an asterisk to it, but that's what you need as a if you want to use these methods for in a practical sense, not if you're not don't care only about strict theory, but you want to calculate, you want to compare with laboratory data and want to do actual science with it rather than pure just theory. That's what you have to do. So there something correction factors, even call it fudge factors, are very useful. So
right.